Hello and welcome back to Introduction to Astronomy. This set of videos is a review for the Unit 2 exam for my students in Introduction to Astronomy. So if you just happen to be watching some of these videos for the fun of it, then skip on ahead to lesson number 15 where we start talking about the sun. So for those of you who are still watching the video, we're going to do a review of these lessons. So lesson 9 was on the formation of the solar system. Lesson 10 was on planetary geology. Lesson 11 was on the Earth and the terrestrial worlds. Lesson 12 was on planetary meteorology. And then lesson 13 was on the gas giants Jupiter and Saturn, the ice giants Uranus and Neptune, and the dwarf planets such as Pluto, and then comets and asteroids. And then lesson number 14 was the hunt for other planets in our galaxy. So let's start off with lesson number 9, the formation of the solar system. Now remember that this test will be about 50 multiple choice questions, and then we'll have about 2 written questions that could either be an essay or a word problem. But if you recall, there wasn't any formulas in this particular series of lessons, so it's going to be essay questions. And then also remember that you get to use the 3x5 index card, and you can put anything that you want on the front and back for that. Now, even if you don't use the note card, it's still a good idea to make it, because that will help you to organize your thoughts and to think about these lessons and what we did in them. So this is chapter 6 out of your textbook. So you should know for the exam the 3 major kinds of objects found in the solar system. So that you've got the terrestrial worlds, which are in the inner part of the solar system. They are relatively small compared to a gas giant. And then their density is relatively high because they're made of rock. And then composition is they're made of rock. And then they tend to have very few moons. Okay, then you should know about the Jovian planets. Now, when I talk about Jovians, I'm talking about Jupiter, Saturn, Uranus, and Neptune. And so they're found in the middle part of the solar system. They are relatively large, roughly 10 times the size, or 10 times the diameter of the terrestrial planets. Then their density is low because they're made of gas and ice. Their composition is composed mainly of gas, so hydrogen and helium, and then the number of moons that they have is going to be many because they have a lot of gravity. Then you have in the outer part of the solar system the planets that are composed mainly of ice and rock. So now we're talking about Pluto, for example. So they are much smaller than the gas giants, and they're even smaller than terrestrial planets. So we're talking about moon-sized objects. Their density is medium because they're composed of both rock and ice, and they tend to have very few number of moons in orbit around them. So from this one here, all I want you to get is just a rough estimate in your head for how large some of these objects are, and it's probably better illustrated in this picture right here, so that you should know that Mars is about half the size of the Earth, and you should know that Venus is about the same size as the Earth, and then, roughly speaking, Mercury is about the same size as our moon. That's very important because if they're small, then that means that they're going to cool off quickly, less geology. And if they have less geology, they're going to have less of an atmosphere. And even if they had an atmosphere, they can't hold on to it very well because they're so small. So having an understanding of the size of these different planets is very important. Okay, then you don't need to know anything about the scaled down version of the solar system, but you do need to know all the parts of the nebular hypothesis. So the nebular hypothesis is this explanation for where did the solar system come from. And so the solar system originates as a nebula, which is this big ball of gas. And you should know that date 4.5 billion years ago. So that's when both the solar system and the Earth began to form. So at about 4.5 billion years ago, you've got this gas cloud, which would have extended all the way halfway to Alpha Centauri. So it's a huge gas cloud, is going to begin to collapse due to gravity. Okay, then the next thing is going to happen is that because this gas cloud is rotating very slowly, as it collapses, those dust and gas particles are going to start to collide with each other. And then because of momentum, as they collide, they're going to change the direction that they're going in, so that eventually this spherical gas cloud is going to collapse into a disk. Okay, now as it's collapsing, the rotation rate is increasing, and this is due to conservation of angular momentum. So angular momentum is the mass of an object times its speed times its radius from whatever it's spinning around. So as the radius is getting smaller because the gas cloud is collapsing, the speed of the gas cloud is starting to increase. Okay, then the disk eventually starts to stabilize at a certain diameter because of centripetal force. So you don't need to know the formula for centripetal force, but you notice that it's got the mass of the particle that's going around in the circle, it's got the speed of the particle, and then it's got the radius of the particle about what it's going around. And so as the R is getting smaller, it's in the bottom part of the formula, which means the centripetal force is getting stronger. And then because the speed is getting larger because of the previous slide, that also means that the centripetal force is getting stronger. So you put those two effects together, and the centripetal force, which is trying to basically, it's not pushing outwards, but it's this force that is, well, take a physics course and you would understand this better, but we're just going to say that the centripetal force is pushing outwards, when in fact it really isn't. But it's going to stabilize this disk at a certain size, so then the planets can begin to form. Okay, now the next step involves temperature. So initially this disk consists of ice and rock and metals and gas, and it's all uniformly distributed in the disk. Okay, but as the thing that's going to become our sun starts to heat up, it's going to start to drive the ice outwards. So the ice cannot exist too close to the sun, so the ice is going to be moved outwards into the middle part of the solar system. And then that means that you still have gas and you still have rock in the inner part of the solar system, and that rock is going to become the terrestrial planets. Okay, the next thing that can happen though is that ice, the dust begins to stick together because of static electricity, and then by the time that the material gets to about the size of bowling balls, it then has enough gravity that gravity takes over as the primary reason for why this material, as it runs into each other, it starts to pile up and eventually we're going to be starting to make moons and protoplanets. Okay, now the next thing that's going to happen, though, is that these protoplanets that are composed of rock start to collect the ice in the middle part of the solar system. So that ice that was driven outwards due to the heat of the sun starts to collect on those protoplanets in the middle part of the solar system. Now you notice that Pluto out there, that little one, doesn't accumulate so much ice because there isn't so much ice out there. It does get ice, but not nearly as much as what the planets in the middle part of the solar system do. And so those get so much ice that they also start to accumulate hydrogen, and so they become the gas giants. And then the final step is that the sun finally turns on and it drives any remaining gas out of the solar system. So this is what you finally end up with, is a solar system that consists of inner planets that are made of rock. In the middle part of the solar system, you've got the Jupiter and Saturn, Uranus and Neptune. And then finally, in the outer part of the solar system, you have rock with a little bit of ice on it, and then that's going to be the trans-Neptunian planets out there. So the planets continue to grow by running into things, and so this takes like another 500 million years for all of the debris in the solar system to get kind of mopped up by all of these planets. But you can still see the effects of this bombardment on the moon today if you look at all the craters on it. And then it is possible for a planet to migrate. So we talked about that in lesson number 14 when we said that Jupiter had the ability to get closer to the sun and then to get further away from the sun. So for right now, we're not going to talk about that, but we will talk about that when we review lesson number 14. And so the remaining debris is in the asteroid belt in between the orbits of Mars and Jupiter, the Kuiper belt, which is outside the orbit of Neptune, and then the spherical Oort cloud, which surrounds the entire solar system. So what is it that causes solar systems to differ? So it's going to depend on what did you have to work with. So what was the composition of the original gas cloud that formed the solar system? It also depends on the mass of that cloud. So if the mass of that cloud is too small, then it doesn't have really enough gravity to pull it in and turn it into a solar system in the first place. It also depends on how fast was the gas cloud spinning, because that's going to control the centripetal force, which in turn is going to control the size of the disk. And then it also depends on the number of stars in your solar system, because they're going to control the temperature of the solar system, and it's also going to control the gravity, which is going to control the orbits of those planets. So you don't need to worry about this appendix thing, but this does, it's a conceptual way of explaining Kepler's third law. Now the actual way of doing it is by using calculus, which you obviously don't need to worry about. But so this slide is not going to be on the exam. All right, so that was a review of that lesson. And so now we're going to come back and we're going to start talking about planetary geology in our next review lesson. So I'll see you there.